Calculus. So these, I think, 6 problems from section 6.5 is really just about understanding notation and how we could represent a Riemann sum without having to actually write out a whole bunch of rectangles. So we understand what summation notation is, right? So what does this horrific mess mean? I mean, this is the kind of thing people look at and they're like, you know what? I don't think so. I'm not looking at that. I was like, who even came up with this? Well, we know who came up with it. Math. And the people who love math. And, people who love math, like us, we really appreciate the precision of notation. It's really absolutely necessary to the project we're engaged in, trying to describe everything that is true and beautiful about numbers in the world, universe, I suppose. So an unfortunate consequence of that, of our desire to have that kind of precision, is sometimes we get this. I think it would be fair to say that we've had a little bit of a blow up here with our notation, just in the sense that the number of places we need to keep track of detail is really, let's say it's proliferated. So what does this all mean? Okay, so what we're doing here is, if we have some function, this is the x squared function, right, x squared, ignoring the k and the asterisk. So, and my a and my b, so I'm going from -1 to 2. So something like that. And just drop those, because we are talking about the area here, right? So what does this mean? Well, so this is a generic expression for a Riemann sum where the number of rectangles, like what does this mean? The max delta x. Well, that's like a delta x is how wide each rectangle is. So Riemann sum can be, I mean, they don't have to all be the same width. It can be some very lopsided, like maybe I've got a partition here, and then I've got another skinny one, and then I've got a wide one here, and then a couple real skinny ones, and then 2 like that. So there's a particular partition, right? There's all the different delta x's. So if we're going to take the limit as the maximum, like the biggest one that there is approaches 0, well, if the biggest one is approaching 0, that's going to force the width of all of them to approach 0. So that's just a way of saying we're going to let the number of rectangles, this is the same as number of rectangles, goes to infinity. It does exactly the same thing. If you force the width of the rectangles to 0, then the number of rectangles is going to go to infinity. So what happens if the number of rectangles goes to infinity? Well, then your approximation here, the sum of all your rectangles, is going to approach the real area, right? If they get skinnier and skinnier, then the little pointy bits, the little sawtooth bits above or below the curve are going to fade away into infinite resolution or something like that. So the number of rectangles is going to go to infinity, the width is going to go to 0, and then we're just going to add up all the rectangles, right? All n of them. Of course, that's going to go to infinity. So what does this mean? This just means any x value in each little subinterval. it doesn't have to be, the reason that we're using this notation and we're being loose here, it doesn't have to be the left endpoint, it doesn't have to be the right endpoint, it doesn't have to be the point right in the middle. It could be any point in there, and this will still work. Why does it still work if you just let it be any x value in each one of the little subintervals? Because as the width of the rectangles is going to 0, that's going to get squeezed, and your any point inside the interval is going to end up just getting squished down, so it doesn't matter. It's going to be the same. We're going to get the same area no matter what. That's the point of that. And, of course, that's the width. So this is the height of each rectangle. That is the width. That's what all that means. So what are we supposed to do here? Well, we're supposed to just be able to look at this and understand it and say, you know, I know a better way of writing this. We are going to look at all that and say, oh, that is, this limit is going to approach the exact area from -1 to 2 under this function dx. That's the answer. And maybe we can appreciate that just like when we take a derivative, like what's going on behind the scenes when we take a derivative? Well, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And then, like, in the meantime, you're saying to yourself, oh yeah, you want to know what the derivative of x squared is? It's just 2x. But this is happening behind the scenes, right? So we need to appreciate and understand and try not to forget that while we're cruising along with our fancy slick notation for area here, this is what's happening behind the scenes. The exact area is defined to be the limit of that Riemann sum approximation where the number of rectangles is going to infinity or where the width of the biggest one is going to 0, which says exactly the same thing. So this is what we're looking for. Okay, so that was a lot of talking about that one. I should be able to cruise through these next ones breezily. So looking at number 6, you've got it there in front of you. I'm just going to go straight to our nice notation. So it looks like my a and b are 1 and 2. So I'm going to say, it's important to be able to look at this and say the right words too. Now this is the integral, or you could say the area at this point, from 1 to 2, the area from 1 to 2, under the x cubed function dx. And I think I mentioned this in the notes somewhere, that now we can kind of appreciate what that dx is. That's like the width of those, right? This is the function value. That's how high it is, and the dx. So that really should look like a height times a width and make you think about the sum of all these rectangles. All right. Number 7, going from -3 to 3. And it looks like my function is 4x times 1 minus 3x dx. And there's nothing else. I don't need to simplify that or try to do it. We're just trying to interpret that notation and write these things down. So 2 ways you could say this. We are going to come to call these things integrals. You could say the integral from -3 to 3 of 4x times the quantity 1 minus 3x dx. You could say that, or you could say the area from -3 to 3 under 4x times the quantity 1 minus 3x dx. And just remember that when we say area in calculus class, that especially if we're around geometry teachers or geometers, you might want to make some air quotes around your area, because for us, area can be negative if it is below the x-axis. And then last one, we've got the integral from 0 to pi over 2 of sine squared x dx. Alrighty. And let's see, 31 and 37. So 31, directions say evaluate the limit by expressing it as a definite integral over the interval from a to b and applying the appropriate formulas from geometry. What means all that? It just means we're going to do exactly the same thing that we just did here, and decode that and turn it into one of these, but then we're going to evaluate it like we did in some other problem sets. So let's see what we got here. We've got the integral 0, 1, 3x plus 1 dx. And that's a straight line, so that should be nice like triangles and stuff that I can do easily. Maybe a trapezoid. So if I plug the 0 in, I get 1. And if I plug 1 in, I get 4. Now, this kind of trapezoid, of course, it's a triangle on top of a rectangle, but we want to get comfortable with our trapezoid area formula. So I'm going to call that, the width of this is 1 over 2. That over 2 is always there. And then in here, I have the sum of the bases, the two heights here. We say bases because when we learn about trapezoids in geometry class, you got one base, the other base, and then like that sort of thing. Of course, for us, so this is like this one rotated like this, and for us, because all of our trapezoids are always sitting on the x-axis, we're going to always be looking like this. So we can have this. Right, that's what we're doing. So that looks like going to be about a 5/2. Number 37. I want to find the largest and smallest values that a Riemann sum can have on the interval from 0 to pi for the function f of x equals sine x. And let me make a sketch of this. Fill in some details from 0 to pi for the sine function. That's like one bump of it. Okay, and then they want the first subinterval is from 0 to pi over 4. And then the next subinterval is 7 pi over 12 wide. The delta x, it's not make a mark at 7 pi over 12. That's how wide the next subinterval is. So let's see. We're already at pi over 4. So pi over 4 plus 7 pi over 12. That's 3 pi over 12. It's 10 pi, 5 pi over 6. So that's just shy of this. No, that doesn't make sense. Hold on a second. Sorry, gears are turning. Sometimes a little bit bigger than. Oh, I guess that's right. Okay, sorry. For some reason, I had myself convinced that that should go past pi. Oh, that's why I'm cuckoo here. This is pi over 2. Right, sorry, this is pi. So it is 5 pi over 6, which is about here. Sorry about that. We're all good. So that's the next subinterval. And then the last one is pi over 6 wide, which of course it has to be if it's going to bring us to here, right? Okay, so there's my 3 subintervals. And they would like us to determine what's the largest and smallest values that a Riemann sum can have. Okay, well, let's see. What's the largest and smallest y value in each one of these? Well, there's 0 here, and then the sine of pi over 4 is the square root of 2 over 2. And then here, of course, that's 1. And then here on this end, this is the sine of 5 pi over 6 is 1/2, which is smaller than that. And then, of course, that's 0 there. So if you wanted to find the largest, then you take the width of each rectangle. So the first one is pi over 4 wide. And the largest, you'd multiply by the biggest value here. So that would be the square root of 2 over 2. Plus the next one is 7 pi over 12 wide. And then what's the highest place, the highest y value you could pick in here? Well, it's that. It doesn't have to be an endpoint, because a Riemann sum can take an x value from anywhere in the interval. That's the biggest one. The biggest one. And then this one is pi over 6 wide. Oh, you can't see anything that I'm writing there. There we go. Sorry. And the biggest would be that. You want to simplify that? Sure, whatever. I'm not going to really see any advantage there. The smallest, the subintervals are all the same width. Can't change that because they told us that's what the intervals are. So if you want to make the smallest, what's the smallest value in each y value in each subinterval? Well, 0. And then here, my choices, I mean, I can choose from anything here, but this is the lowest. And then here, 0. All right. And I mean, neither one of these are particularly good approximations of the area here. I'm going to draw them in. So my largest one looks like this. Oh, there might be just enough juice in this marker here to get something. So this is the largest. Gotta stay inside the lines if you can. Keep coloring. So that is the largest Riemann sum that there is, given these 3 subintervals. And then the smallest would be where's my, there it is. There, that's like no area, and then here, and then here. And we could say that for sure that the real area is somewhere in between that largest one and that smallest one. And of course you can see, you can imagine the area, the real area. That would be in between those. All right, so that assignment was really just about trying to get your head around what that horrific mess means, and maybe it will give us a little bit more of an appreciation for how nice this notation is and what's happening behind the scenes. Just like we have our nice little derivative notation, but this is really what's happening behind the scenes. And it's worth noting that both of the absolute most important cornerstone concepts in calculus, both of those, derivatives and integrals, or area, that both of those are defined in terms of limits. So you think that limit thing's important? Oh yeah, that's why we started with Chapter 2.